Hello, so I'll be giving my presentation on Z transform, and just to give an overview, I'll be going through the definition, initial and final value theorem, and its relationship with the other transforms and how to convert a Laplace transform to Z transform and from Z transform to to the discrete time Fourier transform. So in mathematics and signal processing, the Z transform converts a discrete time signal, which is a sequence of real or complex numbers, into a complex frequency domain representation. It can be considered as discrete time equivalent of Laplace transform. So if Laplace transform is taking continuous time input signals as an input, so the Z transform is taking the discrete time input signals as an input. It is very much similar to continuous time Fourier transform and discrete time Fourier transform. The Z transform can be defined as either one-sided or two-sided transform. The one-sided transform being unilateral or unidirectional Z transform, and two-sided transform being the bilateral Z transform or the bidirectional Z transform. So in the bidirectional Z transform, the Z transform is given by the summation of the input signal and its product with a complex number raised to power minus n, and this n varies from minus infinity to infinity. So that's bilateral Z transform. What happens in unilateral Z transform is that the n ranges from 0 to infinity. So it's not going both ways from 0 to infinity and 0 to minus infinity. It's unilateral. It goes from n equals 0 to infinity. And n is always an integer, so it won't be taking, like, n is not the real number. So now we know how to calculate bilateral Z transform and unilateral Z transform. Now we should know whether they exist or not. So what is the condition for their existence? So for them to exist, they must be less than minus infinity. So the Z transform of the discrete time input signal must be less than minus infinity. So we're just going to apply the bilateral Z transform formula here, and we're going to replace Z by R into e raised to power iota omega. So we'll find out that the magnitude of e raised to power I omega is just modulus of e raised to power I omega is 1, and we're going to be left with this condition. So this condition is the condition for existence of Z transform. Interesting thing here is if we put R equals 1, then we'll get the condition of existence of DTFT. So it's a specific case of Z transform, we can say that in a way. So we can, with the help of an example, we can show how we calculate the condition for existence of Z transform. We check the condition whether it's possible for a discrete time input signal to have a Z transform or not. So we just apply the formula of condition of existence here, that summation over n equals minus infinity to infinity of modulus of the input signal multiplied with the magnitude of the complex number raised to power minus n is less than infinity or not. So we first calculate the summation, and it gives us this value over here. So it's an infinite series, and it has to be less than infinite. For that to happen, we know that the common multiplier must be less than 1. So the common multiplier here is 2 into r raised to power minus 1. So 2 into r raised to power minus 1 must be less than 1, and that will give you r raised to power r is greater than 0. So that explains to us that the complex domain, the signal must lie outside the circle of radius 2. So that's the region of convergence for the example that was given to us. properties of Z transform. We're going to we're going to discuss the initial value theorem over here. So we know the initial value theorem for the Laplace transform. Ft here represents the input signal, and Fs represents the signal after the Laplace transform. So in order to find the initial value of the input signal, that is f0, and like uh, at just after t equals 0, if we're going to find the value of that, then we'll have to take the limit s approaching infinity, s multiplied by the function after having a linear transform over the input signal. So there are a few conditions for that the input signal must be 0 at all times before t is equal to 0, and the input signal must not contain any impulse at t equals 0. So what about initial value theorem for the Z transform? So it's kind of very similar compared to the Laplace transform. The condition for that is the input signal must be 0 at n at all values n less than 0. And if that condition holds true, then x equals x at n equals 0, the initial value of the input signal is going to be given by limit complex number approaching infinity, final signal. It's the final signal, so z must approach infinity in the final signal. So what's the proof of that? So we have a Z transform over here, and its formula, which is going to expand it, and after expansion it comes down to this, right? And one thing interesting to know about it is that n equals minus infinity to n equals 0 terms have been neglected in the summation. Because why? Because all of the terms has to be 0. All of the terms having n less than 0 has to be 0. So that's the prerequisite condition of finding an initial value for the input signal if we're giving the Z transform. So that will be 0. That's why n equals 0 to infinity has been taken here. So yeah, we have this series over here. We multiply the LHS and RHS by limit z approaching infinity. So with that, all of the terms except the first term is going to be cancelled because z comes in the denominator, and all of them are going to be cancelled out, and we're going to be left with the first term, that is the input signal, initial input signal. So it's going to give us the initial value. So this is the proof of initial value theorem for Z transform. Similarly, we can find it for the final value theorem as well. In the Laplace transform, the final value theorem was like this, and the conditions were that the input signal must be 0 at all values of t less than 0, and the SFS must have poles in left half of the S plane. So only then we can find the final value, that is f infinity, and that will be limit s approaching 0 SFS. So what about in Z transform? In Z transform, we're going to see that in order to find the final value theorem, in order to find the final value of the input signal, we must have the following conditions be satisfied first. So the initial value of the input signal in the Z transform must be 0 at all points n less than 0. First condition must be satisfied. The second condition is that 1 minus z raised to power minus 1 xz should have poles inside the unit circle in the z plane. So an interesting thing to note here is that in the Laplace transform we used to have the limit s approaches 0, and here we're having limit z approaches 1. So we must keep that in mind, and while we're solving problems. So just to take an example, and practice the questions of final value theorem. So we've been provided with the Z transform of a discrete time input signal, and we have to find its final value. So we're going to check the conditions first. So the first condition was that all the values of the input signal less than, where n is less than 0, must be 0. So we have not been provided by any region of convergence here. So we have to assume that it is true in this case. So the first condition is satisfied by our assumption that all the values of the input signal where n is less than 0 is 0. So the second condition is that 1 minus z inverse uh, multiplied with the Z transform must lie inside the unit circle. So if we're going to calculate it later on, we'll find that the Z comes out to be like 0. So the pole comes out to be at 0, which lies inside the unit circle. So the conditions are satisfied and we're good to use the final value theorem. So we apply the formula over here and we find the value, right? So it's very easy. So answer comes out to be 1, option C. Now we're going to discuss the relationship of Z transform with Laplace transforms. So if we have to convert a continuous time filter to discrete time filters, that is, if we have to go from Laplace time domain and Laplace domain to Z domain, that is S to Z, we can use this formula over here and convert a continuous time filter to discrete time filter. And we can also do the vice versa with what is shown here. Like we can substitute the value of Z with this expression over here, and we will get the continuous time expression for the signal. And relationship with the Fourier transform is that if we're going to replace Z by R into e raised to power I omega, then if the value of R is 1, that is if the signal is lying on the unit circle, then it converts into the discrete time Fourier transform. So as we can see, if here on the left hand side we have the Fourier transform, not the Fourier transform, the Z transform, and if the magnitude of the complex number is 1, then it turns into a discrete time Fourier transform. So these are the two main relations of Z transform, that is the Laplace, its relationship with the Laplace transform and the Fourier transform. So yeah, that's it. Thank you.